Hello my dear students, please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
In the previous session, we were discussing about the measurement of evaporation. And in the first approach to measure the evaporation or the depth of evaporation from a water body, we have seen about how to install the evaporimeter, that is in the form of a metallic pan whose specifications were rather given by the Indian Standard 5973. So based on that, the pan will be installed just near the water body in which we have to measure the evaporation. And after a certain pre-decided period, let us say a month or a week or maybe a month, depending upon the climate and the the surrounding conditions around the water body, different periods can be set, and after that given period of time, we go back to the evaporimeter pan and notice the lowering of the depth of water in the pan. And then, as I have explained earlier, we need to pour water from the water body into the pan again up to a specified level. There is a standard mark up to which we need to fill the waters. And at the same time, when we fill, this volume of water has to be noted. The volume of water added to reach the stipulated mark divided by the surface area at the rim of the pan, which is a circle whose diameter is 1220 millimeters, will give the depth of evaporation. That is how the measurement of evaporation is done by a pan, which is modified class A pan for the Indian conditions. So sometimes what happens is, during the rainy season, even in the rainy season, the evaporation does not stop. Evaporation is a process which continues 24 hours in a day, 12 months of the year. So it's a non-stop process which continues as long as there is water in the water body. Evaporation will occur. So during the time of monsoons especially, what happens is there is a simultaneous evaporation as well as precipitation simultaneously. In such an event, it becomes difficult for us to, not difficult exactly, but relatively difficult for us to evaluate the evaporation because it is not direct. Direct means whatever the water that has come down in the pan after a certain period, that is refilled. The volume of refill divided by the area of the pan will give us the depth of evaporation directly. Now what happens, what might happen, if it is a rain, if there is a rain around the water body, then this pan, which is open, of course the pan is open to sky. So that pan will also act as a rain gauge and will start collecting the rainwaters. Evaporation and precipitation, they simultaneously occur. In such events, we need to evaluate the depth of evaporation. It won't be a direct measurement, but it will be sometimes we need to do it indirectly. The approach is slightly different, which I shall explain through the numerical problems that we will do a while from now. So let us now review that from the pan, right? If the measurement or when the measurement, okay, is done with the pan, the Indian standard pan, then the depth of evaporation is calculated as E is equals to, let's say, P plus or minus Z. Okay, so here E is the depth of evaporation. P standard is the depth of rainfall. I'll call this as precipitation here. And Z happens to be the equivalent, depth of water added or removed. Equivalent depth. That means when we refill, we are actually measuring not the depth but the volume in the normal circumstances. So that volume of water that is used for refill, sometimes you have to add and sometimes you may need to remove also. When there is, I'll explain that through the numericals again. So that volume divided by the surface area will give us the depth of water that is added or removed. I said equivalent to the volume of water added. Now, how do you calculate this Z? Z is volume of water added or removed depending upon the requirement and the situation, divided by the, I would say, the surface area of the pan. Surface area does not mean the lateral surface area. Surface area means the exposed area of the pan for evaporation. This area, I'll write here, the surface area that I am mentioning here is pi into d square by 4, where this d happens to be 1220 whole square by 4. This is millimeter square. We can simplify that later. You need not actually simplify this, and remember, in the numericals we can easily calculate this. So this is how we calculate the depth of evaporation. We can copy this so that we can do the numericals on this. So let us try to do some numericals on evaporation. So the question number 1, I'll read out the question number 1. The question says, what is the evaporation if 4.2 liters of water is removed from the evaporation pan of diameter 1.22 meters and the simultaneous rainfall is 8.75 millimeters. So in this problem, what is given is, this is problem number 1. Okay, let us now discuss the solution of this problem. The data that is given is volume of water removed. Okay, this is given as 4.2 liters, and we know that 1 liter is 1000 cc, that is cubic centimeters. So this happens to be 4.2 into 10 to the power of 6 millimeter cube. 1000 is cc and 10 to the power of 6 will be millimeter cube. 1 liter is 10 to the power of 6 millimeter cube. Now, diameter of pan, that is standard and mentioned in the problem, is 1.22 meters. This will be 1220 millimeters. Another data given is the simultaneous rainfall. Okay, simultaneous rainfall, P equals to 8.75 millimeters. That is 8.75 millimeters. That is the depth of rainfall. Now we have to calculate what is the value of the evaporation depth. So the question comes, we have to understand the dynamics of this working of the pan, dynamics of measurement. The data says the volume of the water is removed, and the question comes, when do you remove water? Okay, let me explain this through a small sketch. Okay, let us say this is the evaporation pan. Of course, by definition, this doesn't seem like this. This seems to be a container or a vessel. Pan is a shallower depth. But anyway, to understand, I have drawn deeper depth for clarity. Now, for every evaporation pan, there is a stipulated depth. So, let the level 1, this level, be the stipulated mark or the stipulated depth or the stipulated level. Now what we do is we put this water from the water body into the pan up to this mark. Up to this mark will fill. Then the waters will come down. If the waters evaporate, they are bound to come down. Let us say they have come to this level. After evaporation, they have come to this level. So this will give us, this is nothing but the evaporation depth. Agree? But then there is a simultaneous rainfall. There is a loss because of which the waters have lowered, and there is a gain in the form of rainfall which has occurred simultaneously. So the rainfall will add to this, and in this case the waters have gone above this level. The waters have gone above this level. So it has reached level 3. The waters have dropped down. At the same time, the waters have increased. There is a loss, there is a gain occurring simultaneously. But what has happened is the rainfall has been so much that at the end of the day, the waters have gone above this stipulated level. So from here to here, let me mark it here. Okay, so from this stage to this stage, this is P. The evaporation is a loss that has lowered the level. P is the precipitation, which is the gain in the level. So the waters have, this has happened simultaneously. I have been marking it separately here. Is it understood up to here? Now, when the waters go to the level 3, we have to remove the waters, because before we actually measure, we have to bring the water's level to the stipulated level. The water must come back to the stipulated level. Now, it has to come to level 1. So for which we have to remove this portion of water. This portion of water must be removed. So this is the volume of water that is removed. I would mention here, this is volume of water removed. Slowly it is removed from the pan, and that measurement has come to 4.2 liters. So this volume can then be converted into equivalent depth, that is Z. So here you can see that this depth of water that is removed is obtained from the volume of water removed. So divided by surface area, you will get the value of Z. So here, if you want the depth of evaporation, now let us do the calculations here. Depth of evaporation, let it be evaporation here. Depth of evaporation, E, all right, here, E is equals to P minus Z here. Minus because the waters have been removed. This we shall call it as Z. Now if you want E, that is evaporation, that would be the total precipitation that has been caught in the pan minus of the depth of water that is removed. Here, this is, P value is 8.75. And how do we calculate Z? Z is calculated from this formula which I have highlighted. That is volume of water that is removed. That will be 4.2 into 10 to the power of 6. Okay, divided by the area. How much is the area? The diameter is given. This is 5 by 4 into 1220 square. Okay, this is the depth of water that is removed from the pan before the measurement is done, and this gives us 8.75. If you simplify this, you will get around 3.59, right? 3.59. You can check the calculations. So the difference would be 5.16 millimeters, because all the substitution, all the values which have been substituted are in millimeters. Hence, the answer would also be in millimeters. So this is how the pan actually works, how the measurements are done. I would, expect you to copy this as early as possible. Okay, now let us move on and look at what question number 2 has to say. Okay, the next question, that is problem number 2, also deals with the calculation of depth of evaporation, but then the data is slightly different from the previous one. So the question reads like this. Okay, 8.75 liters. This is problem number 2 for you. Problem number 2. Okay, I'll read out. 8.75 liters of water is added to the evaporation pan, of 1.22 meters diameter to bring the water to the stipulated level. If the nearby rain gauge measured a rainfall of 4.2 millimeters, what is the actual evaporation given the pan coefficient as 0.7? That is the question given to us here. Let us look at the solution, but before we solve, let us just write down the data that has been given to us. So here it says, first one, volume of water added. Now this is added. This is 8.75 liters. This much is the amount of water that is added. Why it is added? To bring the, as I said, before the measurement is actually done, we first go to the pan now. Now, on the day we have to measure the evaporation, we go to the pan. Once we go to the pan, we look at the stipulated level. First, we'll notice whether the water is above the stipulated level or below the stipulated level. It may be any case. It may be below the stipulated level or it may be above the stipulated level. If it is above the stipulated level, like in this case, we need to remove water. Agree? But on the contrary, if the level of water is found to be below the stipulated level, then we have to add waters to bring the waters to the stipulated level. And that is precisely what has been given in the problem, that it was found that the level of water during the measurement was much below the stipulated level. That is the reason why 8.75 liters were added to bring the level to the stipulated level. Right? Now, of course, the pan diameter is standard. I'll still write down as a formality that diameter of pan is 1.22 meters, that is 1220 millimeters. So this is given, this is given. At the same time, it says the nearby rain gauge measured rainfall. That means when the rain gauge is measuring a rainfall, that means in the area, in the neighborhood, rainfall has uniformly occurred, and the depth of the rainfall that has occurred in the neighborhood is about 4.2 millimeters. So we shall also mention this here, that the simultaneous rainfall, this is no good grammar to write simultaneous rainfall, but I am just adapting, or rather writing it literally. Simultaneous rainfall, P, is 4.2 millimeters. That is what is given. Now, this is the, the question. let us look at the sketch. Let me do a sketch here. Let this be the evaporation pan. Let this be the stipulated level. Stipulated level. Due to evaporation, the waters have come to this level. That is due to evaporation. The waters have been lowered from level 1 to level 2 because it's a loss of water. At the same time, there has been a rainfall of 4.2 millimeters which has added to this, and the water level then has come to level 3, right? What we have done is, when we have been there to measure, we have observed that the waters are, this is the final level. Level 3 is the final level before measurement. Actually, when we visit, this is the final level. This also is the final level in the previous problem. Now, looking at this level 3, we have to decide whether we need to add or we need to subtract, because the purpose is to get the level back to 1. Now, because level 3 is below level 1, we need to add waters in, and this becomes the set. We have added waters. This is volume of water. I am sorry that I am cramping. Volume of water that is added. This is the volume of water that is added. Why it is added? To get the level from this to the stipulated level. And this happens to be the addition. And the addition is due to the rainfall. P here. So, from here to here in this case would be the evaporation. Because evaporation is from 1 to 2. That is, from this level to this level is the evaporation. Okay. To bring back 2 to 1, the nature has added from 2 to 3 in the form of rainfall, and from 3 to 1 we have added artificially. Are you following? So the sum total of this will give us evaporation. Unlike in the previous case where we are deducting because the nature has added more, whereas we need up to here. So we have to remove this fraction of depth from the pan to get evaporation. So it's very similar. Then therefore we can now write down that the depth of evaporation E is equals to P plus Z, whereas it was P minus Z for the previous data. So here this is P is 4.2 millimeters and Z happens to be, let me write down, 8.75 into 10 to the power of 6 divided by pi by 4 into 1220 square. So this calculation will give us 4.2 plus it comes to 7.74 millimeters, right? So the net value of evaporation. Now this is depth of evaporation from the pan. I haven't mentioned this earlier, but here also, it is from the pan. Okay, you can please note this. E equals to, this comes to 11.96 millimeters. Rather, this is 11.94 millimeters. Okay, but what the question mentions is not the pan evaporation. He says, what is the actual pan evaporation? Sorry, the actual evaporation from the water body. This is the pan evaporation, and we know that pan evaporation is always more than the actual evaporation. So actual evaporation in this case, actual evaporation is equals to Cp, that is pan coefficient, times pan evaporation. Pan evaporation. So this is 0.7 and times 11.94, which comes to about 8.358 millimeters. Okay, so that is what is how we calculate the evaporation. We need to be careful here. We need to decide whether evaporation is P plus Z or evaporation is P minus of Z. We have to first distinguish and then do the calculations. There is a trick here, I can say. Most of the students need to be very cautious here. Caution in the sense, the caution that we need to exercise here is read the problem again. What happens is, I'll tell you, the question is quite simple, but there is a basic difference between the previous question and this question. In both the cases, in the problem number 1 as well as problem number 2, we have calculated the depth of evaporation. But in the previous problem, that is question number 1, we had evaluated pan evaporation. Whereas in this current problem, we are actually evaluating the actual depth of evaporation. If we just by oversight or by some reason or due to the anxiety of the examinations, if you miss the point that is asked in the problem, then you will end up with this answer. We will end up with this answer. That if it is a multiple choice question, one of the choices would be this answer. Are you following what I'm saying? And because of the atmosphere of the examinations, because of the anxiety, if you notice this as one of the choices, you will stop solving the problem there without actually bothering to reading what has been asked in the question. Most of the students tend to miss out on this. So it is always advisable to reread the question before you report the answer. I always suggest my students that if we are really seriously attempting a competitive examination, we have to read the question twice. The first time you read the question is to begin the solution. And the second time you read the same question is to report the answer. Read the question before you report the answer. Anyone, please copy this problem and then we shall move ahead. So do not get confused with this. So copy whatever is relevant. Let us now look at the second approach of estimation of evaporation. If you recollect, right, in the previous session, I had mentioned three different methods or three different approaches to evaluate or estimate the evaporation from a water body. Let me repeat. The first one was evaporation estimation with the help of pan. The second approach, the second method, is based on empirical formulae. And the third method is the analytical method of estimation. Having discussed the pan measurement, we shall now discuss about the various, the second approach or the various empirical methods which are adopted for the measurement of evaporation. The first empirical equation that I would like to discuss is the Fitzgerald equation. Fitzgerald's equation. As we know, this is one of the empirical equations that we have for estimation of evaporation. According to this equation, the rate of evaporation, now this is not the evaporation depth, this is the intensity of evaporation, or in other words, it is appropriate to call it as the rate of evaporation. Intensity is for the rainfall, right? Evaporation, we call it as rate of evaporation. The units mentioned, right, in millimeters per day. This is given by, 0.4 plus 0.124 V, into PS minus PA. Those are pressures, the saturation pressure and the pressure in the air. V is the wind velocity. Let us now write down the various parameters that are involved in the equation. Let me complete writing all that, then I'll give you a chance to copy. Then here you can see this V is the wind velocity in kilometers per hour. This PS in the equation is the saturation vapor pressure in the air in millimeters of mercury, because pressures are always expressed in terms of millimeters of mercury. Whereas this PA is the actual vapor pressure of the overlying air in millimeters of mercury. Hg stands for mercury here, at a specified height of 9 meters. Now this is important, that when we say pressure in the air, actually it is at a specified height. So this pressure difference between the saturation vapor pressure in the overlying air and the pressure in the air at an altitude of 9 meters is measured. The pressure difference is then substituted, multiplied by this factor. This term will give us the net rate of evaporation in millimeter per day. Okay, this is the first empirical equation. The second equation is the MEYER'S formula. MEYER'S equation for estimation of evaporation. This also gives us the rate of evaporation in millimeters per month, actually here is equal to, and let me write down, this is K into PS minus of PA into one more factor, that is 1 in V9 by 16. Okay, so this is the MEYER'S equation. Other than PS, PA and V9, we have a term called as KM. Let me write down the various parameters involved. Where, you can write down where Km is a coefficient which accounts for the size of the water body. And this Km is given as 0.36 for large, deep waters. If it happens to be a very big water body, at the same time, if it is very deep, or relatively very deep, then this coefficient can be taken as 0.36, or it is 0.50. Okay, for shallow waters. The two terms PS and PA are same as that in the Fitzgerald equation, that is the saturation vapor pressure and the pressure in the overlying air at a specified height of 9 meters. This V9, V9 denotes monthly mean velocity. Monthly mean velocity in kilometers per hour at about 9 meters above ground level. So this velocity, which is nothing but the average velocity, okay, for the month at a specified height. The specified height in this case is 9 meters, whether it is measurement of the air pressure or the wind velocity. So this is the MEYER'S equation that is used to estimate the rate of evaporation. Now, sometimes, okay, it is not really easy to measure the wind velocity at 9 meters. We can measure the wind velocity at any depth, at any height, you can say, at any altitude. You can measure the altitude at 2 meters or 3 meters or any depth, and this velocity can be converted into an equivalent velocity of the wind at 9 meters. In other words, we can find out, we can calculate, we can measure the wind velocity at any height and convert it to the wind velocity at any other height, not necessarily 9 meters. We can convert. What we want is at 9 meters, but we can measure it at 2 meters or 3 meters and then convert this value into any other height. If you require at 9 meters, we can also calculate that with the help of what we call it as the 1/7 power law. So I will mention here a small note, because in both these equations we are getting wind velocities. So in that context, the wind speed or the wind velocity can be interpolated. Interpolated means knowing one value, you can convert that into any other value at any other point. So this interpolation can be done using 1/7 power rule or law as V1 by V2 is equals to H1 by H2 to the power of 1/7. This 1 and 2 are nothing but the wind velocities at two different levels, at two different heights. Okay, so here V1 is wind velocity at height h1, whereas V2 is the wind velocity at height h2. So knowing the wind velocity at a particular height, you can convert it to wind velocity at any other height using this interpolation technique. Okay, I would request you to quickly note down what is there on the board. There is one more empirical equation, okay, to estimate the evaporation, and that is the ROHWER'S equation. ROHWER'S equation. This is also an empirical equation to evaluate the rate of evaporation. So he says the evaporation loss in this case is given by 0.771 into 1.465 minus 0.30732 PA times 0.44 plus 0.07334 times V, okay, times, multiplied by PS minus of PA. Okay. So the rate of evaporation by ROHWER'S equation, which is a massive equation, it's very difficult to remember, but still we shall be familiar with what is called as the ROHWER'S equation in evaluation of evaporation. So the rate of evaporation is given in this form. One, if you look at the parameters, PA, V, and PS, they recur in all the empirical equations. PS is, again I'll mention here, PS is the saturation air pressure. This is in millimeters of mercury. That is nothing but the saturation vapor pressure. Whereas this PA is the actual pressure in the air at a specified height. That we have seen earlier. So both are the pressure terms, whereas this V is nothing but the mean wind velocity. Mean wind velocity. Mean wind velocity in kilometers per hour at ground level. At ground level. Okay. Which ground level means? Do you think it is in contact with the ground? No, this is slight height above the ground level, which actually, which can be taken to be, the velocity at 0.6 meters above the ground. So when we say at the ground level, it is not exactly in contact with the ground, but about 60 centimeters above the ground level. Hence, in the formula, you can see this as V naught, V at 0 levels, V at 0 meters from the ground, theoretically, but practically it is about 0.6 meters above the ground. So this is another, equation that is available to estimate evaporation. I would, request you to copy this.